Let's practice predicting the products for reactions for aldehydes and ketones. These examples are found specifically in the in-class worksheet. In the first example that we have a ketone because we have a C double bond O connected to a carbon chain and connected to another carbon chain. Specifically in this molecule, since we have hydrogenation conditions, we need to remind ourselves what's going to happen when I put hydrogenation conditions in the presence of the two functional groups that I have here. In chapter 8, we learned that this is an aromatic ring, specifically a benzene ring. This portion of the molecule is going to be a ketone. And the important thing to remember is that aromatic are resistant to hydrogenation. So in the product of this reaction, specifically, the benzene ring is not going to change. The double bonds present in the benzene ring are going to remain. If instead we would have had an alkene or an alkyne, understand that they would have moved or convert is the correct word into the alkane version for them. But in this molecule, since it's an aromatic, then we don't have to be concerned with that. When it comes to having a ketone, we're going to make the corresponding secondary alcohol. And what happens overall is that I'm going to draw the same number of carbons that we had. I'm going to draw the molecule as it was given. And essentially what's going to happen is that the double bond turns into a single bond. Next, these two hydrogens, one goes to the oxygen, one goes to the carbon that is double bonded to oxygen. And this is the product of the hydrogenation of that ketone. Remember that hydrogenations are also known as reductions. Let's actually look at more formal reductions utilizing sodium borohydride or lithium aluminum hydride. If we have a ketone, like in a reaction 4, remember that that changes to the secondary alcohol. So what I'm going to do with my molecule is that I'm going to redraw it as given. Next, the double bond is going to turn into a single bond. And just like we saw in the hydrogenation, the oxygen will connect with a hydrogen, the carbon in the carbonyl will connect to a hydrogen. Lastly, in reaction 7, we have an aldehyde reacting with lithium aluminum hydride. Sodium borohydride or lithium aluminum hydride do not affect benzene rings. Just like we saw that H2 does not affect benzene rings. So when we look at molecule 7, the benzene ring is going to stay intact. And when it comes to this molecule, I just redraw the molecule that was given. I'm just going to pull it down a little bit down. And overall, in order to predict the products of this reaction, the double bond to oxygen turns into a single bond to oxygen. The oxygen that was in the carbonyl receives a hydrogen. The carbon that was in the carbonyl receives a hydrogen. And that's basically the primary alcohol that forms from the reduction of that aldehyde. Reaction that you see here is not a brand new reaction. We already observed it in chapter 9. Aldehydes can be oxidized into carboxylic acids. And if we look closely into what is the reaction doing specifically, all we can observe is that the carbonyl section of my aldehyde that is connected to a hydrogen, I'm going to, instead of having just the hydrogen, I'm going to connect it to an OH. And that's how we draw specifically the carboxylic acid that forms from the oxidation of that aldehyde. When it comes to the oxidation of ketones, let's understand that ketones cannot be oxidized. And since ketones cannot be oxidized, if you exposed a ketone to oxidizing agents, what's going to happen is no reaction because ketones cannot be further oxidized. In slide 12, specifically, we have the reaction map for aldehydes and ketones to summarize all the discussions that we had for the reactions that you're responsible for knowing. Make sure that you review it when doing your homework. Now we are going to learn about carboxylic acids. Carboxylic acids are organic compounds that contain a carboxyl functional group. To remind you, earlier in the videos, we learned about a carboxyl group being formed by a carbonyl group paired or bonded, I should say, with a hydroxyl group. We also have abbreviated forms to represent the carboxyl group as COOH or CO2H. Remember that they are all covalently bonded to each other. Carboxyl containing compounds are found abundantly in nature. And the tart flavor of foods, which we tasted as a sour taste, it can be because of the presence of carboxylic acids. Many citrus fruits and juices, specifically you can see in the image lemons and limes, come because of specifically a molecule that doesn't have only one, but it has three carboxylic acids. Citric acid, which is present in these products, we can see that it has one, two, three carboxylic acids in its structures. Let's now proceed to learn how to name molecules that have carboxylic acids in their structure. You can see on the left side of the slide where we have the notations on how to name carboxylic acids. I'm going to directly name the two molecules that we have on the right side of the slide to outline the rules that we see on the left. This is a straight chain carboxylic acid. And in this skeletal structure, let's understand that we have to find the longest continuous chain in which carbon number 1 is going to be the carboxyl carbon. So in this molecule, when we explore it, we can see that the longest continuous chain of carbon atoms is going to be 1, 2, 3, 4, 5, 6 carbons in length. So far, we have learned to go from structure to name by identifying in our molecule the prefix, the root, and the ending. And when it comes to carboxylic acids, as we've seen before, the prefix is going to be location and name of the substituent. The root is going to be the alkane name for the longest carbon atom chain. And we're going to omit the letter E at the end. The ending for the name of a carboxylic acid is going to be oic acid. Let's use this information to build the name for this carboxylic acid. The first thing that I'm going to write down is the root. Since I know that this alkane name for 6 carbons is hexane, and I need to omit the E, this will be the word that results. Then I'm going to place the ending, which is going to be oic acid. Notice that there is an intended space. That is not one word. The acid is going to be a separate word. In this molecule, I have 2 substituents. On carbon 4, I have a chloro group because of the chlorine. On carbon 3, I have a methyl group. And remember that those 2 substituents, we have to put them as a prefix of the root and the ending words, and we have to put them in alphabetical order. So we're going to write this as 4-chloro, 3-methyl, hexanoic acid. Remember that the only time that we use hyphens is going to be between numbers and words. So basically, the methyl word in hexanoic is actually together, there's no space between them. So the name of this compound is 4-chloro, 3-methyl hexanoic acid. Carboxylic acids can be aromatic. And when it comes to aromatic carboxylic acids, let's understand that the benzene ring connected to the carboxyl group has a specific name. That whole part of the molecule is actually called benzoic acid. Similar to what we saw in benzaldehyde, the carbon in the ring that is holding the C double bond O is the one that is carbon 1. Then we have to go in the ring clockwise or counterclockwise to see what gives the substituents the lowest number. In this molecule, we must go clockwise. So this is carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Because in the opposite direction, the ethyl group will receive a 3, while the methyl group will receive a 6. So that is too high of a number when we can give it 2 and 5. So since our substituents at 2, we have a methyl. At 5, we have an ethyl group. Let's understand that the name for this molecule, those prefixes need to be placed in alphabetical order. So this molecule, the name is going to be 5-ethyl, 2-methyl, benzoic acid. And that's how you name carboxylic acids. When it comes to the physical properties of carboxylic acids with low molecular weights are liquid at room temperature. And they have characteristically are sharp or unpleasant odors, okay? When we have Acids that contain more than 10 carbons, they actually are like wax-like. They have a more solid consistency. Okay. We're going to learn more about carboxylic acids in biological systems when we are dealing with lipids later in the semester. But for now, to give you an example of a carboxylic acid that is more wax-like, here we have stearic acid. Stearic acid is a carboxylic acid of 18 carbons. And at times it is mixed with paraffin to produce wax, and that is what is used in order to make candles. We can see that depending on the length, specifically of the carboxylic acid, we can see trends. We can observe that in table 10.4, I'm going to zoom in, we have formic acid, which is a carboxylic acid of one carbon, acetic acid, which is a carboxylic acid of two carbons, butyric acid, which has four carbons, valeric acid, which has five carbons, so on and so forth. What we observe is that at least carboxylic acids that have an increase in the number of carbons, we see an increase in boiling point. And overall, when we look at their melting point, we see a decrease in the boiling point. But let's note, the minute that you do the jump from 5 carbons to, for example, 6 carbons, we see that that trend is broken. Okay? The more important thing that we need to know here is that the solubility of carboxylic acids depends on how many carbons are in the molecule. When it comes to carboxylic acids that specifically have 5 carbon atoms or less, so from here down, we see that they tend to be very soluble in water. As I mentioned, carboxylic acids have the highest boiling point of any functional group when they have been studied. One of the important things of why carboxylic acids have that observation is because carboxylic acids can form dimer molecules. What that means is, if we look at the interaction that we see in the bottom of the slide, is that when a carboxylic acid is in the presence of itself, it can actually do hydrogen bonding. And this dimer, which basically dimer means that two molecules, di means two, are going to be bonded together. In the case of carboxylic acids, what we see is that since carboxylic acids can hydrogen bond to themselves, that's why we observe the properties that we observe when it comes to the boiling points. When it comes to simple non-aromatic compounds, the boiling points usually increase in the following order. Hydrocarbons and ethers have less, or in terms of temperature, less boiling point than aldehydes and ketones. Aldehydes and ketones have less than alcohols, and alcohols have less of the carboxylic acids. If you review the content of the material for chapter 9 and the one of this chapter, remember that alcohols and carboxylic acids can do hydrogen bonding events. But the hydrogen bonding that we observe in carboxylic acids is greater because we have the formation of a dimer. We can see in figure 10.24 the trends in boiling points of carboxylic acids when it is compared to other organic functional groups. So as I mentioned, when it comes to carboxylic acids, if you put them in the presence of water, Since they can already hydrogen bond to themselves, they can also hydrogen bond with water. So you observe in the previous table that it says that some carboxylic acid have infinite solubility is because the high level of hydrogen bonding that can happen between the carboxylic acid and in water. Now, carboxylic acids that contain 8 or more carbon atoms are not soluble in water. And as I've explained before, one of the reasons why this happens is because now you have many non-polar character in the molecule, since you have a high number of carbon and hydrogen bonds in the presence of the molecule itself. Since carboxylic acids are known as acids, they behave like weak acids. So one of the things that it is observed is that when a carboxylic acid, in addition to hydrogen bond with water, it can also be deprotonated. Let's understand that the protonation of carboxylic acids in water is a reversible reaction. So even though hydrogen bonding plays a role in the solubility of carboxylic acids in water, in addition, since water can be acting as a base and pull the hydrogen in the carboxylic acid, forming the conjugate base that is known as a carboxylate ion and the hydronium ion. This also explains this solubility. But as I mentioned, when we form this carboxylate ion by water actually reacting with a carboxylic acid, this is reversible. In other words, the reaction is in equilibrium.